Logarithmic differentiation, part 4. A quick reminder of what to do if we have y is equal to a function that has lots of products and quotients, or is a function raised to the power of another function. We want to be able to use log rules, so we'll take the natural log of both sides. Then we'll use log rules to simplify, and then we can take the derivative implicitly, being really careful that we remember that we don't have y equals. It's natural log of y equals. So we have 1 over y times dy dx when we take the derivative of that natural log of y. And that comes from chain rule. And then we have the derivative of this nicer function. Then we just have to make sure we're solving for dy dx. So we multiply both sides by y, and then we know what y is equal to. So we can substitute back in for y. And that's the process that will follow. When we look at this, we see y is equal to a gross mess where we would have to use quotient rule. And inside that quotient rule, we would have product rules. And inside the product rule, we would have multiple chain rules, which is a lot. So we really wish that we had a natural log here, because then we could break up some of these products and quotients. So let's make it so we do have a natural log there. We can't just put a natural log, but we can take the natural log of both sides. So we have the natural log of y is equal to the natural log of the mess, which I'll rewrite slightly so that it's a little bit easier to use our log rules in a moment. So we have the natural log of secant 3x times, well, a square root is raising to the 1/2 power. So we have x squared plus 2 to the 1/2. And this is all over. That is a cosine of x being cubed times an e to the x plus 4. And now we can use our log rules to split this up. So we have, making sure we're really careful to write the natural log of y is equal to the natural log of secant 3x plus 1/2 the natural log of x squared plus 2 minus 3 natural log of cosine of x minus natural log of e to the x plus 4. And we just have to be really careful here that we don't try to split up any sums that are inside of the natural log. We can use log rules to split up products, so things that are multiplied together, and we can use log rules to split up quotients, so things that are being divided, but we don't have any log rules that help us split up the natural log of a sum. But we can still take the derivative now, and rather than having this product and quotient rule, we just have a bit of chain rule. So we have 1 over y dy dx, making sure to take that derivative implicitly, since now we have the function of y as opposed to just y equals. And then, well, we've done a couple derivatives of logarithmic functions, so let's start using our shortcuts a bit. So we have the natural log of secant 3x. Our outside is natural log. The derivative of natural log of something is 1 over that something. So 1 over secant of 3x times the derivative of whatever was inside the natural log. The derivative of secant 3x will be secant 3x tangent 3x, and then times 3 using that chain rule for our third layer, which is the derivative of 3x, plus 1/2 times the derivative of natural log of x squared plus 2. So that'll be the derivative of natural log is 1 over whatever's inside of it. So we have something over x squared plus 2. And then the derivative of x squared plus 2 is 2x plus 0. Minus 3 times the derivative of natural log of cosine of x. So that'll be 1 over cosine of x. is the derivative of the natural log of something. And then the derivative of cosine of x, using our chain rule, is negative sine of x. Then one last derivative. So minus derivative of natural log is 1 over its insides, so 1 over e to the x plus 4, but then we multiply by the derivative of the inside. The derivative of e to the x plus 4 is e to the x plus 0, so just e to the x. And then we can just do a little bit of simplification, and we're trying to figure out dy dx, not 1 over y dy dx, so we'll have to multiply both sides by y. So dy dx will be equal to, well, 3 secant 3x tangent 3x over secant 3x. Our secant 3x's will divide out. So that'll give us 3 tangent of 3x. Plus 1/2 times 2x, we're both dividing by 2 and multiplying by 2. So our 2's will divide out. So we have x over x squared plus 2. And then we have this minus a negative, so we'll end up with plus, and then sine of x over cosine of x is tangent x. So we have plus 3 tangent x. Keeping in mind that this is tangent x while this is tangent of 3x, so we can't really do anything to combine them. And then this e to the x over e to the x plus 4, that doesn't simplify any further, so we just have e to the x over e to the x plus 4. And then we multiplied both sides by y. Then one last step. We know what y is. Y is equal to this mess. So because we have what y is equal to in terms of x, we want to substitute that back in. So we have dy dx is equal to this same 3 tangent of 3x plus x over x squared plus 2 plus 3 tangent x minus e to the x over e to the x plus 4 times y, and y is this secant 3x square root of x squared plus 2 all over cosine of x cubed times e to the x plus 4. So I just substituted that back in for y. And that is dy dx. We have y is equal to inverse secant of x times x root x over sine squared x. Now this doesn't really look as gross as the last function, but it still involves quotient, product, and chain rule. And we want to try to make it so that we involve slightly fewer. So let's use logarithmic differentiation to simplify this a bit. So we'll take the natural log of both sides, and we have the natural log of y is equal to the natural log of inverse secant of x all over, and then just let's rewrite these so that it's a little easier to use our log rules. So x times the square root of x is x to the first power times x to the 1/2 power, which gives us x to the 3/2 power. So that's just my x root x rewritten with a power there. And then sine squared x, that notation means that we have sine of x squared. And that's one of the weird things about notation for trig functions. If we have a positive exponent, a positive whole number exponent, that means that that is actually a power, an exponent that we're raising the function to. But if we have this -1, that means it's an inverse function, not the reciprocal. This means that we have arcsecant. So the inverse of secant, not the reciprocal of secant. So that inverse secant x has to stay in inverse secant x because that -1 is not a power. We can still use log rules to simplify this, though. So we have the natural log of y, being very careful that we keep track of the fact that this is the natural log of y, not just y anymore, is equal to the natural log of inverse secant x minus 3/2 the natural log of x minus 2 natural log of sine of x. And now we can take the derivative. We could have tried to take it before, but it would have been a mess. And we just have to take the derivative implicitly, because this is a natural log of y, not just a y. So the derivative with respect to x of ln of y is 1 over y dy dx. And then we'll use chain rule on each of these pieces. So the derivative of natural log is 1 over what is inside of it. So that's 1 over inverse secant x times the derivative of what's inside of it. And since the derivative of inverse secant x is a quotient, rather than writing it on top of the inverse sine of x, I will write it to the side. So the derivative of inverse secant x is 1 over the absolute value of x times the square root of x squared minus 1 minus the derivative of 3/2 natural log of x, which will be 3 over 2x, minus the derivative of 2 natural log of sine of x, so that'll be 2 times 1 over what's inside of the natural log, so 1 over sine of x, times the derivative of what's inside of it. The derivative of sine of x is cosine of x. And then we need to multiply both sides by y, because we don't want 1 over y dy dx. We want to know what dy dx is. So dy dx is equal to, well, there's not much we can do about this. So we have 1 over inverse sine of x times 1 over the absolute value of x. I will change this to parentheses though. Times the square root of x squared minus 1 minus 3 over 2x, and minus cosine of x over sine of x is cotangent x, so minus 2 cotangent x times y, but we know what y is. Y is equal to this mess. So instead of writing y, I can write what y is equal to. So that'll be times secant inverse of x over x root x times sine squared of x. So this is just my y that I multiply both sides by, and this is the derivative of y with respect to x. That's important.